You did some problems with Coulomb's law. We did some stuff with electrostatics, and now I want to take a minute and do some things where we look at the field. Now you remember when you brought one pen next to the other pen, they didn't have to touch in order to interact with each other. And that's because when you have a charged object, it creates a field of space around it, which basically that's what this talks about. It says that's an energized region of space that exerts a force on another piece. Now, an electric field exerts force on electric particles. We've talked about fields before when we talked about gravity. Gravitational fields exert forces on masses. Now, there is a major difference between electric field and gravitational field, and that major difference is gravitational fields always attract mass. Okay, objects with mass always attract each other. Electric charges don't. Like charges repel. Opposite charges attract. So we have to keep that in mind. Okay. Now this goes on to say, hey, it's a vector. Okay. It's conventional to represent the electric field by a vector called the electric field vector E. In general, it depends on position and time. Yeah, all right, whatever. Okay. Basically, electric fields are going to push on charged particles. They're created by charged particles, and they push on other charged particles. And the amount of push depends on how strong the field is and how big the charged particle is. Okay, just like if you consider an object that's going to fall to Earth, okay, it depends on the strength of the gravitational field, which is constant around Earth. Everything falls towards Earth at the same rate, 9.8 meters per second. But a heavier object has more mass, and more mass means a greater force. Okay, and so not a greater acceleration. So newtons per coulomb is force per charge. Well, if you consider weight, it's really well, not weight, but if you consider gravity, it's newtons per kilogram. Okay, so the more mass there is, the heavier something is. The more charge there is, the greater this force on it is going to be. Okay, and so now we want to look at how we can represent this field, which we do with lines. Okay, now it's important to note electric field lines of positive point away, and the electric fields of a negative point towards. Okay, and that was just decided whenever people were discovering electricity and dealing with that. Okay, so when we take a look at these, you can see positive charge, electric field points away, negative charge, electric field points towards. And basically, electric field lines show the direction of force on a positive charge. Okay, keep that in mind. Okay? It's always relative to a positive charge. Direction of force relative to a positive charge. Now, draw a small circle and a large circle. Alright, so I'm going to draw a small circle right here, and I'm going to draw a larger circle out here. Okay, repeat that process. Small circle, large circle. Excellent. Okay, now what can I say about the number of electric field lines that pass through the large spheres compared with the small spheres? Okay, well, it's the same, right? There's whatever, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. There's 12 lines passing through each one. 12, 12. Okay? The number of electric field lines per unit area through a surface perpendicular to the lines represents the magnitude of the electric field vector at a point on the surface. If you think about what that's saying, it's saying field strength is represented by how many electric field lines go through each section. Okay, so how do the areas of the large spheres compare with the area of the small spheres? Well, this small sphere is small, so it has a small surface area. So larger sphere means more area. Okay. And B, what is the magnitude of the electric field vector far from a charge compared to the magnitude of the electric... Okay, far, it's smaller. Okay, if you think about this, it's because we have the same number of lines spread out over a much greater area. It's sort of like when you throw a rock out in the middle of a nice smooth pond and you get ripples. As the ripples move further from the source, they get smaller. Well, as the electric field gets further from the charge, it's less able to exert force. Okay, so there's more area, but same amount of lines. Okay, and so basically, if you're looking at lines over area, as area goes up, this whole thing goes down. All right. So how do we calculate the magnitude of the electric field? Okay, well, the magnitude of an electric field distance, R, from a point charge Q, is given by this equation, where K is the constant, 9 times 10 to the ninth, and Q is the absolute value of the charge. Okay. Now, it's interesting to note that this is absolute value of charge, but this is a vector. Okay. So anyways, we're supposed to copy this equation in. The electric field vector is equal to K, okay, Coulomb's constant, 9 times 10 to the ninth, times Q times nothing over R squared. Okay, now this looks a heck of a lot like Coulomb's law, right? Coulomb's law said F equals K Q1 Q2 over R squared. The difference is we don't have this R2, this second charge. This is the field strength. It's not describing a force. It's describing a force per coulomb. How much force could be felt on something because of it. Okay. Now, if more than one point charge is present, electric field lines are going to mangle each other. They're going to get together. They're going to push on each other. They're going to pull on each other. But essentially, it's going to be like if two people are pulling or pushing on one object, it's going to go in the direction of the net force. Okay, and so that's what this is about. So this says Q1 is plus 5, and this says Q2 is negative 6, and these are microcoulombs, so times 10 to the negative 6. Okay, and this is centimeters. We got to keep that in mind. But we're supposed to draw and label electric field vectors E1 and E2 on point P. Now you'll notice this is not a charge. It doesn't have a charge. It's just a point. Okay, so if we think of this thing, it's got electric field lines that radiate and point away from it. Okay, and so there's an electric field line that comes off of P pointing away from Q1. This is E1. Okay. Similarly, Q2 is right here. It's got electric field vectors that head towards it because it's negative. Okay. Now, actually, I'm going to go ahead. I'm going to redraw this a little bit because E2 has a bigger arrow because it's a bigger charge. Okay, so it's going to have a slightly stronger electric field. Okay, I know it's more negative, but hey, its overall value is bigger. Remember, it's an absolute value thing. Okay, so we've got Q1, we've got Q2, and I'm going to split this page so I can look at both this information at the same time. Let's see. How do I do that? Oh, right there. I want dual page display. Okay, and let's jump over to the next page. Now I know that just got kind of small, but it says calculate the magnitude of the electric field E1 at point P due to Q2 and the magnitude of the electric field at E2 at point P due to Q2. Alright, let's go back to a one-page display. We need a couple numbers, right? We know that Q1 is equal to plus 5 microcoulombs. We know that Q2 is equal to negative 6 microcoulombs, and we know the distance between any of them is 0.35 meters because it said 35 centimeters. Alright, so now let me go back to one page and let's do some math. Calculate the magnitude of the electric field E1 at point P due to Q1. Okay, so electric field, the magnitude does not include a direction, is equal to K, 9 times 10 to the ninth, times Q, 5 times 10 to the negative 6, that's what micro means, divided by 0.35 squared. And if we do this math, we'll see that this works out to be 367,000 newtons per coulomb. Okay, now I did round that a little bit, 367,346, okay, which is closer to 347 newtons per coulomb. Okay, we have to do a similar process over here. So E2 is K, 9 times 10 to the ninth, okay, times 6 times 10 to the negative 6 okay, microcoulombs divided by 0.35 squared. And again, when we work this out, we're going to get a fairly large number, in fact, a little bit larger than before. 440,816, okay, 440,816 newtons per coulomb. Okay, so what this means is for every coulomb of charge that comes into this field at this point, it's going to feel 367,000 newtons. Every coulomb of charge that comes into this field at this point will feel 440,000 newtons of force. Okay. Now we're supposed to calculate the x component and the y component of the electric field vector E1. So E1x and E1y. Now if you remember our picture, in fact, let's just jump back to it for a second. Okay. E1 is pointing this direction. We need a positive x and a positive y. Well, generally speaking, we keep things orthogonal. Here's x, here's y. This vector points a little bit this way and a little bit this way. We know this angle. Why do we know this angle? Well, it told us this was an equilateral triangle. This is an equilateral triangle. That means this angle is 60 degrees. And these being vertical angles, that's also 60 degrees. Okay? And so I'm going to draw that picture. I've got this thing going this way, okay, and so this is 60 degrees, and this right here we know from E1, this is 367, 347. We want the x and y components. Well, this is a right triangle. We want the adjacent side, so 367, 347 times the cosine of 60. Right? Adjacent over hypotenuse is cosine. I want adjacent side is going to give us that answer. Okay? So 367 times 347,000 times the cosine of 60, making sure that we are in fact in degrees. Let me check that real quick. Mode, degrees, awesome. Okay? And that gives us 183,000, okay, newtons of force. Okay? 183,000, and this is an x, 183,673 newtons per coulomb. Okay, now be careful. This x component is actually this direction, which is positive. Okay, so I'm okay with that. But my y is going to be negative. And of course, I'm going to do the same thing, only instead of cosine, it is sine, right? Because sine is the opposite side. So second enter, changing my cosine to sine, and I get 318,132. 318,132 newtons per coulomb. This one is negative because it is going down. Okay, we're supposed to repeat step 3 for E2. Well, this is a heck of a lot easier for E2. E2 is this way. Okay, it's 440,000, but it is negative. It's to the left. So negative 440,816 newtons per coulomb. And 0, right? There is no y component of it. That's just handy. So add them up and see what we get. Since E1 is to the right and E2 is to the left, these are going to act against each other. So negative 440,816 plus 183,673 gets us negative 257,143. Negative 257,143 newtons per coulomb. Okay, and this one, there's only one in y, and it's negative 318,132. Okay, and so the total electric field is going to actually be ending up going down and left. Okay, so it says determine the magnitude and direction of the resultant electric field. Okay, well our x is this way, 257,143. Our y is this way, 318,132, okay, and our resultant vector is the vector sum. It's this way, okay, and so we can use the Pythagorean theorem. So 257,143 squared plus 318,132 squared, and square root that. That gives us a magnitude of 409,000. Okay, 409,000. 0.60 newtons per coulomb, and I want this direction, theta, so I'm going to use the tangent, well, the arctangent of opposite 318,132 divided by 257,143, okay, and that gives me 51 degrees. So the direction is actually technically measured from here. Okay, so all the way around, that's 180 plus 51, and that gives us 231 degrees. Okay, 231 degrees. All right, it's vector addition. I know it's been a while since we've done that, but that's how that works. Okay, and so this tells me if a charge is at point P, it's going to feel 409,000 newtons of force for every coulomb of charge that it is in a direction of 231 degrees. Okay. This is kind of interesting to draw electric field lines when you have multiple charges, okay? But it's really not bad if you think about it. Okay, Q1 is going to have an electric field line that points away from it. Okay, Q2 is going to have electric field lines that point towards it. And since these are equal charges, right, plus Q minus Q, they should have equal number of lines. Well, what's going to happen between them? Well, this field line is going to go from here to there, and if we had one that was trying to go this way, it would get pulled towards Q2. So this is sort of what this one looks like. Okay, these ones are both positive. Now it says these can't cross, so this one and this one and this one are relatively unaffected. Okay, but what happens when I have this field line that tries to go this way and this one that tries to go this way? Well, those ones are going to hate each other. Okay, and so they're going to like push each other parallel, and we're going to get electric field lines that look goofy like that. Okay, they don't cross, but they do push against each other. Okay, these ones are both negative, right, and equal charge. So we're going to have sort of the same thing, only instead of this charge pointing away from the charge, it points towards it. Okay, and so these are going to be coming in like this. It basically looks just the, whoops, that one would be fairly straight. It basically looks the same as the positive, only in a reverse direction. Okay, and we might have one coming in that way. And finally, this one is positive and this one is two negatives. Okay, well, this positive one is going to have field lines coming in towards it. Okay, and this will jump across, and this one will bend in, and this one will bend in. But this one is bigger, so it's going to have more lines coming in towards it. And this might be able to push it more like that, okay, and more like that. I'm not going to get too worried about that. Just remember that this one's going to have a bigger effect. Okay, so those are the electric field lines, or something like that. Now, finally, an application of electric field lines. Okay, in each of the diagrams, we're looking at electric fields. Okay, the electric field lines are uniform and constant. Well, that's true of one, but it is not true of two. Right? This is changing. If we draw a line here and a line here and a line here, we have the same number of lines per unit area. If we have lines here, okay, for every area here, they're different. The electric field line is produced by a single point charge. Neither. Okay, a single point charge would have things extending radially, and none of these are radial. Okay, these are parallel. These are coming together. It can't be a single charge. The electric field becomes stronger left to right. Well, this one's uniform, but this one from left to right, we're getting less area, same amount of lines. So 2, that's true. The electric field is produced by some arrangement of positive charges on the left. Well, if these are positive, electric field lines should point away. They do. If these are positive, electric field lines should point away. They do. So both, 1 and 2. Electric field is produced by some arrangement of negative charges on the right. Well, if there's negative charges, they should point towards. They do. They do. So again, both. All right. Now, this second part I'm going to go ahead and split into a different video. It's a little bit different. It says, all right, well, let's look at what happens when a charge actually moves through a field. It's sort of like when you move a mass against gravity. So we're gonna get electric potential energy, which is of course going to require some work.